In this video, we'll be talking about extrinsic semiconductor. We also call it doped or impure semiconductor. Now, what is an extrinsic semiconductor? And to define the extrinsic semiconductor, it's a semiconductor obtained after adding some suitable uh, impurity atoms in the intrinsic semiconductor. So we have the intrinsic semiconductor, and we add the suitable. The point is suitable, impurity. Now this is a pure semiconductor. So when we add uh, some amount of impurity to a pure semiconductor, uh, uh, impurity atoms in the semiconductor, it becomes an extrinsic semiconductor, and we call this as extrinsic or doped semiconductor. And so we can say here that the process of adding some suitable impurities in the intrinsic semiconductor is called doping. Now, intrinsic semiconductors, as we already know about them, they have thermally generated current carriers, right? And at room temperature, we have electrons available in the conduction band. Now, if the temperature of this intrinsic semiconductor is increased considerably to have more and more charge carriers in order to increase its conductivity, it may get damaged. So to increase the conductivity of an intrinsic semiconductor, some suitable impurities ought to be added, and we can add some suitable impurities. So this small amount of impurity that we add here, this changes the conductivity pattern of these pure semiconductors, and this process of doping causes change in the carrier concentration of these semiconductors. Now, this doping there can be many ways by virtue of which this doping can be carried. To talk about it in a trivial sense, we can add a very small quantity of impurity atoms, and we can diffuse them into high purity molten material such as germanium or silicon, right? So when we diffuse them into the crystal lattice, this causes the change in the conductivity of these materials. There can be another way, like the impurity atoms can also be added into the intrinsic semiconductor by heating it in the environment having impurity. So having impurity in the environment, right? And there can be another important way that can be used is we can bombard the parent intrinsic semiconductors with the impurity atoms, and we can have the doping using bombardment of atoms on the material. Now the question arises that this doping, I mean, can we add anything that we want to add to the parent material? And the answer is no. We cannot do that. So we have to be cautious when it comes to the point of doping. I mean, the very important point regarding doping is that the size of dopant atoms, it should be it should be of the order of the size of the atoms of the parent material. So we cannot have a dopant of any size that we can use uh, in a semiconductor. So the dopant has to have a size which is very much comparable to the size of atoms that are there in the parent semiconductor material. So a dopant atom, they are supposed to take the place of the atom. So if there is an atom X, when I use a dopant, it has to replace this atom from the parent matrix. So here is what it becomes important is that you cannot use all the dopants to do the job. There are necessary points to be considered while making doping possible for these semiconductors. So the addition of impurity atoms in the intrinsic semiconductors, it should not change the basic structure of the crystal lattice. So suppose we have an environment like this, we have a dopant, and this dopant will replace an atom, right? So it's not going to change the phase of the system. It should not change. It's not going to change the basis of the system. So the number of dopant atoms should be about 1 in a million parent atoms. So this is an important point. 1 in a million parent atoms. So we can understand that how small this doping is actually in its quantity when it talk about the quantity of these dopants. Now the impurities that we add to these intrinsic semiconductors. These impurities can be of two types. One is pentavalent pentavalent impurities. Now, what are these pentavalent impurities? Uh, the atoms who have 5 electrons in their valence shells. And the examples of these dopants are um, arsenic, uh, As, then we have antimony, and then we have phosphorus. These are the examples of pentavalent dopants that we can think of using for intrinsic semiconductors. And then the next class of impurities that we can think of are trivalent impurities. Now, trivalent impurities, and the examples of these trivalent impurities are indium is an example. Okay, gallium is an example. Okay, aluminum is an example. Boron is an example. So these are the atoms, the impurity atoms who have a valency of 3. And in case of pentavalent impurities, we have the atoms like arsenic, antimony, and phosphorus who have 5 electrons in their outermost shells. Now, when we dope a parent intrinsic semiconductor, say we have intrinsic semiconductor, and let us take a formal lattice for an intrinsic semiconductor like that's made of silicon atoms, right? So if we take a network like that, suppose we have a silicon, then we have another silicon, then we have another silicon, we have another silicon, then we have another silicon, then we have another silicon, then we have another, another. Now, as we understand from electronic configuration point of view that the silicon has four electrons in its outermost orbit, so it has four electrons, and between these four electrons, there are covalent bonds, right? So we have covalent bonds between these silicon atoms, like this. So this is my what should I call here? I have a situation like this. Okay, I have a situation like this. There are bonds between them. There are bonds between silicon atoms. So there is mutual sharing of these electrons, right? Now, when we make use of, I can do it like this as well to make it consistent with what I'm doing here. So if I do it like this, this is a pure intrinsic semiconductor. Now, what am I going to do is to replace this silicon, say for example, by indium. Now, indium is what? Indium is a pentavalent. It's a pentavalent atom. So when I do that, so when I replace this by indium, what happens is indium has five electrons. So four of its electrons will make the bonds with the network ahead of it, and the fifth electron will be left as its. So what's going to happen here is that we will have, when we will make use of indium in the network of silicon atoms, we are adding an electron to the original matrix. So here we're going to say that that this type of semiconductor, which has been doped by pentavalent impurities, this type of semiconductor is called as p-type, sorry, n-type semiconductor. So what is n-type semiconductor? N-type semiconductor is a semiconductor that's doped by pentavalent impurities, and it has majority of electrons in it and minority, because we know that minority of holes, because we know that semiconductors have have two types of charge carriers. One is electrons and another is holes. So this way we are able to enhance the conductivity of the original silicon matrix by adding pentavalent impurities to the original matrix. Now, proceeding on, so this type of semiconductor is called as n-type semiconductor. Now, on moving from here, so what is important about this type of doping is that we have excess of negatively charged electrons in the matrix of pure semiconductor, and this is what makes it a p-type semiconductor. And we can reveal the situation in terms of energy band diagram. Now, if I take a situation like this where I have I have been talking about this is, say for example, this is my these are my levels up to the valence band, and then I have the conduction band. So this is valence band and this is conduction band. Now this thing I'm revealing at the temperature greater than that of 0K. So at the temperature greater than that of 0K, we understand we have the presence of what we call as electrons in the conduction band. Uh, but now what we have done is we have added the impurity to this network of silicon atoms. So what's going to happen here is that the energy level corresponding to the holes in p-type semiconductor, it lies just above the valence band. So the impurity atoms that we have added, they are going to generate an energy level, and that energy level is it has to be in case of in case of n-type semiconductor, it has to be uh, close to the conduction band. So this should be the case here, that we have the what we call as the energy level of the atoms that we have introduced into the network. They are going to create an energy level, and that energy level is close to the conduction band, and this energy level is called as donor level. We call this as donor level. So there is a mediation now. There is a mediation. So we have an energy level which is called as donor level at the temperature greater than that of 0 Kelvin, and its value for silicon is it's nearly this Eg that we have here is nearly 0.05 electron volts. So you have the valence band. Okay, in the valence band we have electrons there, and the electrons leave from here and they create holes in the valence band, and these electrons are available in excess in the conduction band in case of n-type semiconductor. So to talk about this in a very trivial way, we are doping here by a pentavalent impurity. So the fifth electron in the n-type semiconductor, it occupies a discrete energy level, right? And that level, what I was talking about, is the donor level, which is just below the conduction band of the semiconductor crystal. The energy gap between the donor level and the conduction band is very small. It's very small, okay, and it's of the order of 0. For silicon, it's of the order of 0.01 electron volts, and for germanium, it is of the order of 0.05 electron volts. So even room temperature provides the sufficient thermal energy to the free electrons uh, to to at donor level to jump to the conduction band. So when if your electrons are here, but at room temperature, they will have the sufficient thermal energies so that these electrons are available in the conduction band. So this type of material that's over here, we call this type of doping is n type of doping, and the semiconductor that we have obtained from doping the pentavalent impurity, we call this as n type semiconductor. Now the same story goes uh, with uh, with with p-type semiconductors. Now, in case of p-type semiconductors, what we have what we have in case of p-type semiconductors, we are doping the original network by the trivalent impurities. So the trivalent impurity is going to, so you have the bonds, the covalent bonds between these silicon atoms, and and what you are going to do is you are replacing this silicon by virtue of doping, and putting a trivalent impurity. So the trivalent impurity that we have is indium or gallium. So let us suppose it is indium. I think in the previous case, I might have committed a mistake in case of when I was talking about pentavalent impurity here. Okay, it has not to be indium, because indium is a trivalent impurity. Okay, and indium is a trivalent impurity. So here we are using pentavalent impurity. So it should not be indium. It should be arsenic, or it should be antimony. Okay, the atom that will replace silicon in this case has to be pentavalent. So indium is not a pentavalent impurity; it's a trivalent impurity. So this thing needs to be corrected. That here we are making use of. We are not using indium here. We are using, say, for example, arsenic, which is pentavalent in nature. So here we are using indium. So once we use indium, what's going to happen is you are going to develop a hole in this network, right? So by developing the holes means you are increasing the number of holes in the original matrix of silicon network, and this kind of doping is called as it's a trivalent doping. And in this case we have holes as majority charge carriers, number one, and electrons are minority charge carriers, right? So this is the case here, that you are replacing the atoms by trivalent atoms like indium, gallium, uh, uh, aluminum, etc. Now, moving forwards, let's talk about this. So this type of extrinsic semiconductor is called as p-type semiconductor. This is called p-type semiconductor. Now, moving on, if we think of an energy diagram for this p-type semiconductor, if we think in terms of energy diagram for p-type semiconductor. So let's go with what we are showing here is for the systems at greater than zero. So we have valence band, okay, and we have conduction band. Say it's like this. This is my conduction band, and this is my valence band, and there is an energy gap. Now we have added the impurity, and this impurity generates what it generates an energy level, and that energy level is close to the valence band, and that energy here is called as acceptor level. So, so what's the story about this p-type of semiconductor? Is that this energy level diagram corresponding to the holes, in the semiconductor, it lies just above the valence band. So it's very close to the valence band. So here we have an energy, right? Say that energy is EA, right? So this energy level that we have here, as I told, this is called as acceptor energy level, and the energy difference between acceptor level and the highest energy level of valence band. This is the highest level of the valence band. Is much less than the forbidden energy gap. Okay, so if we see the original forbidden energy gap in a pure semiconductor, say for example for silicon, this energy gap is nearly 1.2 electron volts, right? And for germanium it's nearly zero point 0.7 electron volts. But if we talk about the energy level that has been introduced by doping as an acceptor level, the energy difference between this acceptor level and the valence band is very small. It's of the order of the same thing, 0.01 electron volts for silicon. Okay, so at room temperature, the thermally generated electrons in the valence band are easily transferred to the acceptor level, and hence large number of holes are created in the valence band. Okay, so you are taking electrons to the acceptor level, and the large number of holes are created in the valence band, and these holes act as current carriers when p-type semiconductor is connected across an external battery source. So, in case of p-type semiconductors, the conduction is primarily because of holes. The majority current that you say is due to the holes, and the minority current is due to the electrons, right? So minority current. So the point of discussion here is that when a suitable pentavalent impurity is added to pure germanium or silicon crystal, we get an extrinsic semiconductor known as N-type semiconductor. And when a suitable trivalent impurity is added to pure germanium or silicon, we are able to get the p-type of semiconductor. So that should be the case. That should be the point of distinction between a p-type semiconductor and N-type semiconductor. Now the question is that both N-type and p-type semiconductors, they are neutral. For example, when we add pentavalent impurity atoms or added in germanium or silicon crystals, electrons of the donor atoms they are simply donated for easy conduction through the germanium or silicon crystal. Each donor atom that we add to the matrix, it has a neutral charge, so it does not add any charge to the semiconductor. As such, the donor electrons are the part of the impurity atoms and do not make N-type semiconductor as negative. Similarly, p-type semiconductor has access holes as compared to the electrons. Since all the atoms in the p-type semiconductor are neutral, so p-type semiconductor as a whole is also a neutral system. So that should be something to be borne in mind at this stage. And if we talk about the Fermi level, the Fermi level that we might be discussing in future, there is a Fermi level. It lies in the forbidden energy gap near the valence band in case of p-type semiconductor. So if we define the same thing for in terms of the Fermi level, for that, if the Fermi level is close to the valence band, then this is a p-type semiconductor, and if the Fermi level is close to the conduction band, then this is an N-type semiconductor, right? So this is the story, should say, uh, of the extrinsic semiconductors. Now we can understand that we can modify the characteristics, we can modify the properties of these materials by making use of the dopants, the doping elements, and these dopants, their concentration, their type, they can certainly change the conductivity of these materials, and having the conductivities that we are interested in can be attained using those dopings.